identical particles. We can discuss identical particles in classical mechanics and identical particle in quantum mechanics. The identical particles in classical mechanics are distinguishable. But the identical particles in quantum mechanics are indistinguishable. Don't worry, I will tell you what is meant by this. Identical particle. What is identical particle? Suppose there are two balls. Okay, these are two balls of the same company. So they will be looks same, right? Identical, right? So here these two balls are distinguishable. Okay, you will get more idea when we are discussing about indistinguishable particle. Okay, in quantum mechanics, two identical particles means I am taking two electrons. Okay, two electrons are there, and we know the de Broglie theorem. That is lambda is equal to h by p. That is mv, and we know the mass of electron is very small. So the wavelength of electron will be large. Similarly, we can consider the wave function of these balls in classical mechanics. That is lambda is equal to h by mv, and the mass of these balls are very high when comparing to the mass of electrons. Okay, therefore lambda will be very small. So these are the two particles, and if you are considering these two particles, then there will be an associated wave function look like this one. Okay, so here this is the distance between two balls, average distance between two balls. So here these are the wavelength lambda, and you can see this average distance between two particles is very much higher than the wavelength, right? So it is distinguishable. This is the condition for distinguishable particle. And here you see the wavelength of each of these electron is very high. So it will like this one. And for the other electron, the wave function will look like this one. So when we are seeing these two electron, we observe a common wave function. Okay, so this is the distance between these two electrons, average distance between these two electrons, and this is the wavelength. Here you can see the wavelength are overlapping, and due to this overlap we will observe this two as a single one. So we cannot distinguish each of these electrons. That is the condition for indistinguishability is average value of separation between these two is very much less than lambda. This is the reason why electrons in an atom is observed as a electron cloud. We cannot distinguish each of the electrons. And in quantum mechanics, the indistinguishable particles are two types. One is fermions, and second one is bosons. So the fermions obey Fermi-Dirac distribution, and bosons obey Bose-Einstein distribution. Or statistics, okay. And what is this fermions? We know spin of a fermion is n by 2 h cross. That is n will be 1, 3, 5, etc. Only odd values. And the fermions obeys Pauli's exclusion principle. Can you say an example for fermions? The example is electrons. And bosons. For bosons, the spin is equal to NH cross, where N is equal to 0, 1, 2, etc. And these bosons don't have any restriction. And the example for boson is photons. Okay. Here, what is this Pauli's exclusion principle? Pauli's exclusion principle. This principle is applicable to fermions only. And we know electrons are fermions. Maybe you are already familiar with this principle. That is, no two electrons can have all the same quantum numbers. That is, if all electrons or all fermions are in same spin state. That is ket S ms. Then maximum number of fermions in a state will be equal to 1. And if all these fermions are in different states, different spin state, that is, and if S value is equal to n by 2 h cross, then if S is equal to half h cross, then 2s plus 1 is equal to 2. Where this 2s plus 1 is the degeneracy. That is, degeneracy is equal to 2. And if S is equal to 3 by 2 h cross, then 2s plus 1 is equal to 4. That is, degeneracy is equal to 4. And if S is equal to 5 by 2 h cross, then 2s plus 1 is equal to 6, and the degeneracy equal to 6. Maybe you have some doubts. I will tell you little more explanation. That is, what is spin state is equal to half h cross? Suppose this is the axis and this is S vector, that is half h cross. The length of the vector is half h cross. So it can take two orientations. One is plus half and the other is minus half. That is, ms is equal to plus half. Here ms equal to minus half. So two states are possible. That is why we got degeneracy is equal to 2. That is, two states have same energy. And here this is z axis and this is S equal to 3 by 2 h cross, the length. So it can have different orientations like this one. That is, there are 4 orientations are possible. This is corresponds to plus 3 by 2 h cross, and this one is corresponds to plus 1 by 2 h cross, and this one is corresponds to minus half h cross, and this is corresponds to minus 3 by 2 H cross. Okay, that is, there are 4 states. All these 4 states have same energy. That is, degeneracy is 4. Wave function of fermions and bosons. So this particle have certain spin. So the total wave function is equal to psi space into psi spin. So spin has certain wave function and the space part. That is, if particle is moving in space, so there will be a space part of wave function will be there. So the total wave function of a fermion or boson will be psi space into psi spin. And there is a speciality, that is, for boson particles, the total wave function psi total should be always symmetric. So the symmetric is represented by a plus sign. And the fermions always have a psi total, that is antisymmetric or asymmetric. That is represented by minus sign. I tell you how this minus sign and the plus sign differentiate this symmetric and the asymmetric wave function. Okay. So for a boson particle, the total wave function, that is, total wave function is space part into spin part of wave function. Okay. And that will be symmetric for boson particles, and that should be asymmetric or antisymmetric for fermions. Suppose this is the wave function of a boson. So I told you the wave function of a spin particle have a two part. One is psi space and one is psi spin. So if the space part of wave function is symmetric, then the spin part also should be symmetric. Then only the product of these two will be symmetric. And if space part is antisymmetric, then spin part also should be antisymmetric. Then only the total wave function will be symmetric. Okay, and in a similar way for fermions, if space part, so I told you this will have a space part and the spin part, because this is a particle with a certain spin. Okay, so if the space part is symmetric, then the spin part should be antisymmetric or asymmetric. Okay, then only the total wave function will be asymmetric. And if space part is asymmetric, then spin part should be symmetric. Okay, please remember this criteria, that is, total wave function of a boson is always symmetric and total wave function of a fermion is always asymmetric. Okay, now let me introduce a particle exchange operator. That is represented by P12. Suppose this operator is operating on certain state psi of x1 comma x2, where x1 and x2 are the position of two different particles. Okay, so when this particle exchange operator operates on some state, then the state become x2 x1. See, the particle position is interchanged. Okay, and when this exchange operator operating on the state, the resultant may be positive or negative. Positive means it is symmetric and the negative means it is asymmetric. Now let us consider some examples of symmetric and asymmetric wave functions. The first one, that is 1 by root 2 psi 1 2 plus psi 2 1. See, here there is sign is positive. That means this is symmetric wave function. Earlier I told you, if the signs are, all the signs are positive, then that wave function will be a symmetric wave function. And this one is normalization constant. That is 1 by root 2. Okay. Second one, 1 by root 2 psi 1 2. And now I am using the particle exchange operator. So it becomes psi 2 1. But when this particle exchange operator is operated on the state, it becomes negative. That means it is a symmetric wave function. And one more example, that is there are particles 1, 2, 3, and the particle exchange operator is operating on this. So I got psi. Now I am exchanging these two. Okay, that is 2, 1, 3. Now again the particle exchange operator is operating on this state. So again we got negative, and now I am exchanging these two. That is psi 2, 3, 1. Now we are operating particle exchange operator on these two. So we will get minus psi 3, 2, 1. Now we are operating parity operator on these two particles. That is plus psi 3, 2. Then operating on these two, then minus psi 1, 3, 2. So there are total 6 steps. So when we are normalizing, we get a normalization constant 1 by root 6. And see, there are negative signs. Therefore, this is asymmetric or anti-symmetric wave functions. One more example, that is 1 by root 6 psi 1 2 3 plus psi 1 3 plus psi 2 3 1 plus psi 3 2 1 plus psi 3 1 2 plus psi 1 3 2. See, all are positive. So this is symmetric wave function. Earlier I told you particle with a spin have two wave functions, that is psi total is equal to psi space part of wave function into spin part of wave function. So first we are going to discuss about space part of wave function. So I told you there are two type of wave function will be there. One is symmetric and another one is asymmetric. So in this section we will discuss both the symmetric and the asymmetric wave function, that is space wave function. That is, if particles are arranging in a space, then how we can represent their wave function. That is the idea. Okay. So first I am going to consider there are two particles in a state, in a single state. That is, this is the state, some single energy level, and there are two particles I am representing as psi 1 and psi 2. So the total wave function is a combination of wave function of these two particles. Okay, that is psi. And here we will have the symmetric part of wave function, that will be equal to psi 1 of first particle, this particle, into psi 1 of second particle. Okay, so this is wave function of the first state. Okay, this state. So the first particle is in psi 1 state and the second particle is also in the psi 1 state. Okay, this one is also in the psi 1 state. So we got the symmetric wave function, that is psi 1 of 1 into psi 1 of 2. And now let us check what will be the asymmetric wave function. Is there will be any asymmetric wave function? No, it is not possible. That is an important note. If all the particles are in same state, then the function is always symmetric. Okay, please remember this. Next, we are going to consider two particles and the two states. That is, there are two states. I am calling the first state as psi1 and the second state as psi2. And the two particles are phi1 and phi2. Okay, suppose in this condition, each particle is in each state. Okay, so maybe the first particle will be in the first state and the second particle will be in the second state, or second particle will be in first state and the first particle will be in the second state. Here these are identical particles, so we cannot distinguish which one is in the psi1 state and which one is in the psi2 state. But we know one particle is there in psi1 state and another particle is there in psi2 state. So maybe first particle is in the psi1 state and the second particle in the psi2 state, or second particle will be in the psi1 state or first particle will be in the psi2 state. Okay, that is why I took both the combination. So the wave function, you can write the symmetric wave function, that is psi1. So this is the first state. So in this state there is a particle, phi1 particle. So I am calling psi1 of 1. That is the space part wave function of this particle. Okay. Now I want to consider the second particle, that is this one, right? That is in the psi2 state. So psi2, in psi2 state, second particle is there, that is psi2 2. And there is another combination is also possible, that is this one. Okay, so I am using this symmetric wave function, so I am using plus sign. Now in the first state, which particle is there? Second particle is there, right? That is psi1 of 2. And the second state, that is in psi2, which particle is there? First particle is there. Okay, and this is not normalized wave function. So for normalization, I am using a normalization constant, that is 1 by root 2. See, this is symmetric wave function, that is why I use this plus sign. So here the particle state may be a combination of these two. Okay, that is why we use this plus sign. That is symmetric combination. Now I can consider the asymmetric wave function. That is, nothing is there, 1 by root 2. The sign only will change. That is psi1 of 1, psi2 of 2 minus psi1 of 2, psi2 of 1. So this is the corresponding asymmetric wave function for this two particle in two states. Let us consider one more example. So if you have any doubt, you can clarify from this example. That is, now we are going to consider three particles. Three particles and two states. And here I give you some more condition, that is two particle are in one state and one in other state. Here the condition is each state has each particle. Okay, that is why there is no combination like See, psi 1 here, psi 2 here, or psi 1, psi 2 here. Okay, that condition is excluded by this condition, that is each state has each particle. Okay, so this is not possible. So this is the only two combination. Now there are three particles and two states, and two are in one state and one in other state. Okay, so these are the two states. State is psi 1 and other is psi 2. And there are three particles, right? I'm calling the particles are psi 1, phi 1, phi 2 and phi 3. So what are the possible combinations? Now I'm filling this phi 1 and phi 2 here and phi 3 here. Now what is the other combination satisfying this criteria? That is psi 1, psi 3 maybe in the first state and phi 2 in the higher state. Or there is one more possibility is there, that is phi 2 and phi 3 are in first state and phi 1 is in the next state. Okay, so these three combinations are possible for this given condition. Okay, now we can write the wave function, that is symmetric wave function, that will be equal to, so first this is the state, that is psi 1, and in psi 1 there are two particles 1 and 2, that is psi 1 of 1 and psi 1 of 2 into, now in the another state psi 2 there is one particle, that is psi 2 3. Here we are considering the symmetric wave function, so I am using the plus sign. Now the other combination, that is this one. So in the state psi 1 the particle is there, that is psi 1 1, and the third particle is also in the same state, that is psi 1 3, and this particle, second particle is in psi 2 plus the last combination, that is psi 1. In psi 1 there are two particles, that is 2 and 3, into psi 2 state there is one particle, that is first particle. Okay, so this is the symmetric wave function and it is not normalized, and the normalization constant is 1 by root 3. So the number of times is the normalization constant. Now let us consider the corresponding asymmetric wave function. So the asymmetric wave function will be 1 by root 3 psi 1 1, psi 1 2, psi 2 3 minus psi 1 1, psi 1 3, psi 2 2 plus psi 1 2, psi 1 3, psi 2 1. Earlier also we seen that for asymmetric wave function the sign is plus and minus sign is alternative. Here maybe you have a doubt how we got this normalization constant. So the normalization, I tell you an expression, normalization for space part wave function is that is n equal to, n is the normalization constant, that is equal to root of n1 factorial, n2 factorial, n3 factorial, etc. by n factorial. Here what is this n1, n2? These are number of particles in each state. I tell you, don't worry. Okay, and the capital N, this one, N is total number of particles. Now let us consider this as an example, this wave function. So we got a normalization constant as 1 by root 3. Here, what is the number of particle. So n1, that is 2 particle. In the state psi1, there are 2 particle, right? And in second combination is n2, then in n2, that is in the second state, only 1 particle. Okay, and total number of particle, capital N, is 3. So what is the value? N is equal to root 2 factorial into 1 factorial by 3 factorial. That is root of 1 into 2 into 1, right? By 1 into 2 into 3. So we can cancel this one. So we will get 1 by root 3. Okay, that is why we got normalization constant n is equal to 1 by root 3. Okay. And fourth example. So in this example, there are 4 particles in 2 states. And the condition is each state has 2 particles. So there are 2 states and the corresponding wave function of the states are psi1 and psi2. And there are 4 particles. So these are the 4 particles. Okay, and there is a condition each state has 2 particles. Now I am calling these particles are phi1, phi2, phi3 and phi4. Right, and there are 2 states. Now I am going to fill this particle in these states. So first I am taking first particle in the psi1 state, and the second particle is also in psi1 state, and taking third particle and fourth particle in the psi2 state. Or maybe, see, these are the identical particle, so other combinations are also possible. Now I am using particle exchange operator. So I am going to exchange 2 particles. These 2. I am keeping the first particle there itself, and I am interchanging 3 and 2. Particle 3 and 2. Now again I am going to use particle exchange operator. Now I am going to interchange these 2. That is, one is there, 4, 2, 3. And I told you, suppose this is plus, then when we are using this particle exchange operator and for an asymmetric state, this become negative. Okay, and again I am using the particle exchange operator, so I'll get positive sign. That is, I told you, if particle exchange operator is operating on a state that is 1, 2, then we get minus psi 2, 1. This is the condition for asymmetric operator, right? So now again I am going to use this particle exchange operator. Now I am exchanging 1 and 3. That is 2, 1, 3, 4. So I got a negative sign. Again I am interchanging 2 particles. That is, I am taking 4 and 2. So 3, 2, 4, 1. See, it become plus. Now I am interchanging these 2. So 3, 4, 2, 1. That become negative. Is there any further combination is possible? No. Okay, if you are again interchanging, you get the same combination. So these are the various different combinations of or arrangement of these 4 particles in these 2 states. And here we need to know the normalization constant n in order to write the wave function. That is, we know root of n1 factorial n2 factorial by n factorial. Here what is n1? That is number of particles in the state 1. That is 2. And what is the number of particles in the state 2? That is 2. And what is the total number of particles? That is 4. Therefore, we will get n is equal to root of 2 factorial by 4 factorial, that is equal to 2 into 2 by 1, 2, 3 into 4, that is 1 by root 6, right? So we can write the asymmetric part of wave function, asymmetric wave function of space part. That is equal to, the normalization constant is 1 by root 6 into, first we have to consider this combination, that is in the psi 1 state particle 1 is there, and in the psi 1 state particle 2 also there. Okay, into, in the psi 2 state particle 3 is there, and the psi 2 state particle 4 is there. Now we are going to consider this one. So there is a minus sign, minus, in psi 1 state particle 1 is there and the particle 3 is there, and in psi 2 state particle 2 is there and the particle 4 is there. Now we are considering this combination, that is plus, in the psi 1 state particle 1 is there and the 4 is there, and in the psi 2 state particle 2 is there and the particle 3 is there, minus. Now we are taking this one, that is why there is a minus sign. Okay, so you please fill the remaining terms also, and you can write the symmetric wave function by 1 by root 6 and use all are positive. Okay, here substitute plus and here also plus, and all the terms have a positive sign. Then you will get the corresponding symmetric wave function of space part of these particles. Here we are discussing about wave function of identical particle with the spin. Okay, so the total wave function is equal to space part of wave function into spin part of the wave function, because the particles have spin. Okay, so there will be a corresponding wave function for the spin of the particle, right? So we already discussed about space part, right? Now we are going to discuss about spin part of wave function of, first one, fermions, and then about bosons. So here we are first going to discuss about fermions, that is space wave function of fermions. And here we are discussing, our discussion is exclusively on spin half fermions, that is electrons, right? So let us consider two spin half fermions. So first particle has a certain spin, that is half, and other particle is also have spin, that is half. So here there are two particles are there. So if these particles are interacting, then spin coupling will happen and we will get spin, the net spin of these two particles as S1 plus S2 to S1 minus S2. That is S1 plus S2 is half plus half, that is 1, 2. S1 minus S2, that is half minus half, that is 0. That is S equal to 1, 0. Spin after coupling of these two particles is 1 and the 0. And if S equal to 0, we say it is a single state, and the multiplicity will be 2s plus 1, that is equal to 1. So we call this as singlet state because there is only single state, and the single state is asymmetric state also. And there is other combination, that is s equal to 1. For s equal to 1, the multiplicity is 2s plus 1, that is 3. So corresponds to s is equal to 1. There are 3 states. So this is triplet state. And the states are symmetric states. This is very important information. Okay. Here I will give you little more explanation for singlet and a triplet state. That is, two states are there. S1, that is half, that magnitude of that state is half. Okay, spin state is half. And another state is there, and the magnitude of that state also half. Okay, so we can take, suppose I am considering a vector for this one and another vector for this one. So the magnitude of this vector is half half, right? And you can see this vector can have two orientation, that is ms values, that is ms will be plus half, that is orientation is plus, and ms can be minus half, that is orientation is like this one. Okay, minus negative direction. So the magnitude only we are discussing as s1 equal to half, and ms discuss its orientation. Maybe this plus half, this is plus, okay, this is minus half. Okay, so s is the magnitude and ms is the orientation, plus or minus. Here also ms value is, one is plus and the other is minus, that is plus half and the minus half. So now we are adding s1 magnitude and the s2 magnitude. Now we are not bothered about the direction. Okay, so what is the magnitude? One is half s1 plus s2, that is half plus half, and other combination is s1 minus s2, that is 0. So the net magnitude of spin is 1 here, that is mentioned as capital S, that is 1 here, and net magnitude of spin here it is 0 after the coupling. Here also these are the magnitudes. Magnitude of this vector, the resultant vector. This vector can have different orientation. Okay, so the magnitude of vector is 1, but it can have different orientation. For s equal to 1, it will have 3 orientation, that is this may be the s equal to 1, or this may be the s equal to 1, or this may be the s equal to 1. So this is the origin, right? So about origin, there will be 3 orientation for s equal to 1. All these 3 vectors have same magnitude, but direction is different. Okay, all this will be in a circle. So each of this vector, the direction or orientation of the vector is represented by capital ms value. Here we use the small ms. So after coupling, we use the capital values. There is capital ms is here plus 1. Here capital ms, there is projection of this vector, s vector, on this axis. See, this axis is 0 for this one, right? That is ms equal to 0. And here this is ms equal to minus 1. So for s equal to 1 vector, there will be 3 orientation, that is ms value plus 1, 0, and the minus 1. And here the magnitude is 0, right? So ms value is 0 only. That is, this is the axis. So the magnitude of s is 0, right? So the projection on this axis is also 0, that is ms equal to 0. Okay. Here, what we are discussing? We are discussing about spin wave function, right? And how we can represent the spin wave function? The spin wave function is represented by chi s ms. Here we are discussing with the two spin half particle, right? And I told you this two spin half particle, after coupling, it may be in a singlet state or it may be in a triplet state. So each of these particle have S1 is equal to magnitude. Spin magnitude is half and S2 is half. Okay, after coupling S, we get capital S value, that is 0 or 1, right? So singlet is corresponds to capital S equal to 0 and triplet is corresponds to capital S equal to 1. And I told you the single state is asymmetric state and the triplet state is symmetric state. That is the wave function also symmetric. And I told you for S equal to 0, the capital MS value will be equal to 0, and for triplet state, the capital MS value will be 1, 0, minus 1. So we can represent this singlet and triplet state using this notation, that is X, here S value is 0 and MS value is 0. And here there are three states corresponds to this one. Chi, S is 1, MS is 1, and for this state, chi is S is 1, MS is 0, and for this one, chi 1 minus 1. So this is the representation of spin wave function of singlet state, and these are the spin representation of triplet states. Okay. And earlier I told you the orientation of spin may be plus half, that is in the positive direction, or minus half, that is in the negative direction. So the plus half is represented as alpha and the minus half is represented as beta. Here see, in the singlet state, the ms value is equal to 0. That is, what is ms value? Ms is equal to ms1 plus ms2. That is equal to 0. And how we will get this value? Ms, that is ms1 plus ms2 equal to 0. Here, what is this ms1 value? ms1 value can have plus half or minus half. So if ms1 is plus half, that is upspin. Okay. And ms2 is minus half. Then adding plus half and minus half, we will get 0. Or first particle may be in spin down state and the second particle is in the spin up state. So then also when adding plus half and minus half, we will get 0. Okay, so these are the two possible combination of particles which give the total ms value is equal to 0. And here we cannot distinguish which particle is in the spin up state and which particle is in the spin down state. So we have to take combination of these two. Okay, that is these two expressions. That is, here first particle is in the up state, right? Spin up state, and the spin up state is represented by alpha, that is alpha of 1. And this particle, second particle is in the spin down state. Spin down state is represented by beta, that is particle 2 is in spin down state, that is beta. And here I told you this is a symmetric wave function, therefore the sign will be minus. Next combination, that is this combination. So first particle is in spin down state, that is beta of 1, and the second particle is in the state spin up state, that is state is alpha, the particle number is 2. See, this is not normalized wave function. So we have to normalize. That is, number of times in this wave function is 2. Therefore, 1 by root 2. And this wave function is represented by chi 0, 0. That is the wave function corresponds to singlet state. Now we have to find out wave function of triplet state. That is this one, and this one. Similar to singlet state. How it is possible? Here I am first time taking ms value equal to 1. So first case ms value is equal to 1. How I can make ms value equal to 1? That is, ms is equal to ms1 plus ms2. That should be equal to 1. That means ms1 is in spin up and this one is also spin up state. So we will get 1, right? ms equal to 1. Adding this half, we will get 1. So spin up state represented by alpha, and first particle is in spin up state and the second particle is also in spin up state. And this wave function is represented by chi 1, 1. Now we have to consider the second ms value, that is ms equal to, we know ms1 plus ms2 is equal to 0. So the possible combinations are, first particle may be in spin up state, second particle is in spin down state, or first particle is in spin down state and second particle is in spin up state. So this is corresponds to plus half and this is corresponds to minus half. So adding we get equal to 0. This also equal to 0, right? So there are two possible combinations are there, and we can represent the first combination as, first one is alpha, that is spin up state and particle is 1, and the second one is spin down state, that is beta 2. And here I told you this is symmetric state, right? Therefore symmetric state, the sign will be plus. And second one is this combination, that is beta 1 alpha 2. And we have to normalize this wave function. So there will be 1 by root 2 time, and this is represented by chi 1, 0. Now we have to consider the third case, that is ms value is equal to minus 1. That is ms equal to, we know ms1 plus ms2 is equal to minus 1. So the possible combination is, this will be down and this will also down. The first particle and the second particle are in spin down state, right? Okay, so we can represent the states are beta of 1, beta of 2. That is represented by chi 1 minus 1, right? So these are the 4 states. So I'm rewriting those states, that is there are 2 particles with a spin half is there, okay, and there will be 2 states. One is single state and other is triplet state. Single state corresponds to s value equal to 0 and triplet state corresponds to s value equal to 1. And the single state is a symmetric state. Triplet state is symmetric state. And we got the wave function for single state, that is chi 0, 0. This is the representation, and this one is ms value and this is s value, right? That is equal to 1 by root 2 alpha of 1 beta of 2 minus alpha of 2 beta of 1. So there is only one state for s equal to 0, and for s equal to 1 there are 3 states, and those states are represented by chi 1, 1, that is alpha of 1, alpha 2. That is, both the particles are in the spin up state. Now, second one is 1 minus 1. That is beta of 1, beta 2. That is, both the particles are in spin down state. And the third one is 1, 0. That is 1 by root 2 alpha of 1 beta of 2 plus alpha of 2 beta of 1. This is symmetric state, that is why plus sign. Here this is asymmetric state, that is why this minus sign. Okay. So these are the four wave function of two spin half particle. Here we are discussing about wave function of identical particle with the spin. So the total wave function contains a space part and a spin part. So we discussed how we can write a space wave function if states are given and the particle number of particles is also given. And just now we discussed how we can write spin part of fermions, right? So in this session we are going to find out the total wave function, that is the product of space part and the spin part. Now let us discuss about helium atom. That is He2O4, right? And first we are considering ground state of helium atom. That is, ground state is 1s2 state, right? That is, in the s subshell there are 2 electrons, and we know these electrons are fermions. That is spin half fermions, right? And we found, just before we found the wave function of all the four wave function of spin half fermions, right? So we are going to use those expression here. So this is the condition. The state is single state. 1s is a particular state, right? And in that particular state there are 2 electrons. That is 1 and 2. These are the electrons, and that particular state is represented by psi 1. That is, 1s state is represented by psi 1, and the electrons are represented by phi 1 and phi 2. Now first we are going to write the space part wave function. That is, so this is a 1s state, right? So in 1s state, psi 1s state, particle 1 is there, and in psi 1s state, particle 2 is also there. So both the particles are in the same 1s state. So this is the wave function, and this one is symmetric wave function. Earlier I told you, if there is only one state and 2 particles are there, then only symmetric wave function is possible. There will not be any asymmetric wave function, because there is no way to write minus sign, right? You have to interchange the particle, then only we can write the minus sign. Here we can't interchange the particle, so there is no asymmetric space wave function for particle in a single state. Okay. Now we got the space part wave function. So in order to find out the total wave function, we have to find out spin part also. How we can find out spin part? That is spin part. Here we are discussing about electrons, that is fermions, and earlier I told you a condition for fermions, the total wave function should be symmetric. And for bosons, the total wave function should be symmetric, right? So in order to make total wave function asymmetric, there is 2 possibilities. One is space part will be symmetric and the spin part should be asymmetric, or space part should be symmetric and the spin part should be symmetric. Here for space part, asymmetric space part is not possible. Okay, so this is not possible. So the spin part should be asymmetric, right? So what is the asymmetric wave function for two fermions? That is x 0 0 singlet state, right? That is, this is the asymmetric wave function, and singlet state is 1 by root 2 alpha of 1 beta of 2 minus alpha of 2 beta of 1. So the total wave function, now we can write the total wave function, that is psi total is equal to space part, that is psi 1s of 1 psi 1s of 2 into 1 by root 2 alpha of 1 beta of 2 minus alpha of 2 beta of 1. That is, we will get psi total is equal to 1 by root 2 psi 1s of 1 psi 1s of 2 alpha of 1 beta of 2 minus psi 1s of 1 psi 1s of 2 alpha of 2 beta of 1. Okay. This is the wave function for ground state for a helium atom, right? Now let us consider the first excited state of helium atom. That is 1s1, 2s1. Okay, one of the electron is in the 1s state and another is in 2s state. That is like this one. This is state 1s and this is 2s. So in the 1s state there is one electron and the 2s also one electron. And this may be, first electron may be in the 1s state and the second electron in the 2s state, or second electron in the 1s state and the first electron in the 2s state. So this both combinations are possible because this is identical particle. We cannot say which one is occupying 1s state and which one is occupying 2s state. So this both combinations are possible. Maybe first particle is in the 1s state and the second particle is in the 2s state, or first particle is in the 2s state and the second particle is in the 1s state, right? Here we are discussing about electrons, that is about fermions. For fermions, we know the total wave function should be asymmetric. So for total wave function should be asymmetric, the conditions are space part into spin part. So if space part is symmetric, spin part should be asymmetric, or if space part is asymmetric, spin part should be symmetric, right? So first we are going to write the symmetric space part, that is psi space symmetric. What will be the symmetric space part? That is, symmetric means plus sign, and here there are two possible combinations, this one and this one. So we can write this as 1 by root 2 into, here first particle is in the 1s state and the second particle is in the 2s state, plus, because this is a symmetric combination, right, plus first particle is, sorry, second particle is in the 1s state and the first particle is in the 2s state. So we got the symmetric space part. Now we have to find out the asymmetric spin part, that is equal to, you know, there is only one asymmetric spin part for two fermions, that is 1 by root 2 alpha 1 beta 2 minus alpha 2 beta 1. So we get the total wave function is equal to psi space part, that is symmetric space part, into psi spin part, asymmetric spin part. Okay, so you just multiply these two equations, you will get the total wave function. So we got one of the combination, this one, right? Now we have to check the other combination, this one. That is, here space part is asymmetric, right? This is first one. Now we are going to find out the second one. That is, space part is should be asymmetric. That is, nothing is there. We have to interchange the sign. That is 1 by root 2 psi 1s 1 psi 2s 2 minus psi 1s 2 psi 2s 1. And now we have to find out the spin part, a symmetric spin part, right? Then only we get the total wave function as asymmetric. So what are the symmetric spin part for two particles? We know there are three combinations are possible. That is, one is alpha 1, alpha 2, and the other one is beta 1, beta 2, and other one is 1 by root 2, alpha 1, beta 2 plus alpha 2, beta 1. This is the triplet state, right? Symmetric spin part of two fermion is triplet state. So multiplying this time with this one, you will get one wave function, and multiplying this wave function with this one, you get another one, and multiplying this one with this one, you will get another one. Okay. So there are total three wave function we will get. And see, all the three different wave function have the same energy. Therefore, we can say degeneracy of first excited state of helium atom is 3. Why? Because all the three wave function have same space part, right? And the space part of wave function is corresponds to energy. Spin part is not a contribute to the energy. Only space part of the wave function will contribute to energy. And for all these three wave function, the space part is same. Okay, therefore all the three state have same energy. Therefore, the degeneracy of first excited state of helium atom is 3. Here we are discussing about wave function of fermions, right? That is electrons. And we already discussed a case of helium atom. And we find out the total wave function. So the total wave function consists of two parts. One is space part and the other is spin part. So the electron have a spin and it is also rotating about the nucleus. So there will be two parts of wave function. One is space part of wave function and other is spin part of wave function. And we already seen the wave function for these electrons. That is, this electron in ground state of helium atom. That is in the 1s state. That is, two electrons are occupied in 1s state. And we write down the corresponding wave function for spin part and space part, and we found out the total wave function also that we already discussed in the earlier lecture. Now we are going to write those things in a easier way. So here I am going to introduce later determinants. By understanding the method of Slater determinants, you can easily write the total wave function of large number of electrons. Here only 2, but writing this 2 electron itself is a difficult thing. So if there are 3, 4, 5, 6 electrons, then writing the wave function will be little more difficult. So in order to simplify it, we have Slater determinants. So I am starting with an example, that is helium 2. And earlier we already solved this problem, that is 2 electrons are in the 1s state. That is, there is only single state and both the electrons are in same state. And the state is 1s state, right? So we can write its space part. Here both the electrons are in the same state, so only symmetric part is possible. So the symmetric wave function for this particle is psi 1s1, psi 1s2. That is, both the electrons are sitting in the or occupying the same state 1s, psi 1s, right? So we know the total wave function should be asymmetric for fermions. So if space part is symmetric, then spin part should be asymmetric. Then what will be the spin part of wave function? Electron wave function, that will be asymmetric one, right? That is singlet state, right? That is 1 by root 2 alpha of 1 beta of 2 minus alpha of 2 beta of 1, where I told you alpha is upspin. That is, first particle is in the upspin, second particle is in the downspin. Here second particle is in the upspin and the first particle is in the downspin. Okay, so this is the asymmetric spin part. So we can write the total wave function, that is equal to psi space into psi spin, that is 1 by root 2 alpha of 1 beta of 2 into psi 1s of 1 psi 1s of 2 minus alpha of 2 beta of 1 psi 1s of 1 psi 1s of 2. So this is the wave function, total wave function, right? Here what I am going to tell you is, we can write this wave function in very easy way by using Slater determinants. See, this total wave function we can write in a determinant form. How? That is, psi total is equal to 1 by root 2 into determinant psi 1s of 1 alpha of 1 psi 1s of 2 alpha of 2 psi 1s of 1 beta of 1 psi 1s of 2 beta of 2. Suppose if you are multiplying this determinant, that is, see, multiply this way, that is psi 1s of 1 alpha of 1 into psi 1s of 2 beta of 2, that is the first time, right? Minus this one, psi 1s of 2 alpha of 2 into psi 1s of 1 beta of 1, that is nothing but this time. So we can write this wave function as a determinant form, that is this one. So here let us check what is the property of this determinant. The properties. So by identifying these properties, we can write any wave function as a determinant form, Slater determinant form. Okay, so the first property is, if n is the number of particles, then the determinant will be n by n determinant. Here there are 2 particles, so we got 2 by 2 Slater determinant. Okay, second one, normalization constant. See, what is the normalization constant? That will be 1 by root n factorial. Here there are 2 particles, so 1 by root 2 factorial, that is 1 by root 2, right? Third property, This is about rows. In the rows, you can see same states. See, this one is psi, oneness of alpha of 1. Alpha 1 means upspin, right? And here psi oneness of 2 into alpha of 2. That is, particle is in the upspin. Okay, so this space part is psi oneness in both case, and the spin part is upspin in both case. That is, I am telling the rows have same state. Here, the state is psi oneness. Here, spin state is down, right? Here also this space state is psi oneness. Spin state is down state, right? So both the states are same, but particle arrangement is the only difference. So this rows contains same states. Fourth property, columns. Check in the column. In the column, see, particle number 1. Here also 1, 1, 1. So in the first column, all the particles are first particle, right? And second column, see, all the particles are second particle. So the column contains same particles. So this is the properties of Slater determinant. So if you know these 4 properties, you can write wave function of any particles, any fermions, right? Now let us discuss some examples. First example. As first example, we are taking the earlier case, that is, in the psi 1 state, there are 2 particles, phi 1 and phi 2. By the Slater determinants, we can write the total wave function, that is product of spin part and the space part, as a determinant form. Okay, so the determinant contains, there are 2 particles, so the determinant will be 2 by 2 determinant. Okay, and we know the normalization constant is 1 by n factorial, that is 1 by root 2 factorial. Now we have to fill the determinant. Now by using this rule, we can write, or we can fill the rows. That is, rows contain same states. That is psi 1 alpha, psi 1 alpha. And other row contains psi 1 beta, psi 1 beta. Now we have to fill the particles. That is, column contains same particle. So first column contains first particle. Okay. Second column contains second particle. So we got the Slater determinant. So by Slater determinant, see, we got the product of spin part and the space part. So by using Slater determinant, it is very easy to solve. Now let us discuss another example problem. That is, there are 2 states, psi 1 and the psi 2, and there are 2 particles, phi 1, phi 2. Here in the second problem, by writing this Slater determinant, we will not get the exact wave function. The reason is, in the second case, there is no Pauli's exclusion principle. That is, you see, in the first example problem, if one of the electron is in the upspin, then the other one definitely in the downspin. Or if it is in the downspin, then second particle will be in the upspin. So it is satisfy the Pauli's exclusion principle, because both the electrons are occupying the same state. Both the electrons or fermions are occupying the same state. But here, these 2 particles are occupying different state. So the first particle can have upspin, at the same time second particle can have upspin, or first particle can have downspin, at the same time second particle also can have downspin, or this one is up, this one is down, or this one is up, this one is down. So all these possibilities are there. Therefore, actual wave function we will obtain, total 4 wave function we will obtain. That is, earlier I told you. In the case of helium atom, we considered the first excited state. So in the first excited state, we got 4 total wave function. Are you remembering? Okay. So for this case, this determinant is not completely written, but we can write some part of it. That is 1 by here root n factorial, that is 2 particles are there, 2 factorial, and there are 2 particles, so the determinant will be 2 by 2 determinant, and the condition, third condition, that is rows same states, columns same particle. So these are the same states, phi 1, phi 1, and rows same state, right? And now you have to fill the particles, that is in column same particle. So this will be 1, this will be 1, this will be 2, this will be 2. But this is not complete wave function, total wave function. The reason is there will be 4 total wave functions because it is not completely determined by the Police exclusion principle. It is not valid. The Police exclusion principle is not valid here because both are occupying different states. Okay. So the stated determinant for such cases is this one. Third example problem. That is, there are 2 states, psi 1 and psi 2. In the state psi 1, 1 particle is there, and in the state psi 2, there are 2 particles. Now we have to write the stated determinant for this one, that is 1 by root. The normalization constant will be number of particles factorial, that is 3 factorial here, into determinant of so this one will be a 3 by 3 determinant, right? Because there are 3 particles. So first we are considering this state and these 2 particles. So maybe this one is first particle, this is second, third one, or we can interchange these particles, okay, because these are identical particles. So first I am going to write this one. For this case, it can have any state, upstate or downstate. But here there is a restriction. If this particle is in upstate, the other will be downstate, and if this one is in downstate, the other will be definitely in upstate. Okay, but for this particle, it is not a problem. It can have any state. So we are not specifying the spin state of particle in the psi 1. That is psi 1. There are 3 row will be there, 3 column will be there, right? And we know in the row all the states will be same. So I am filling the same states. And in the second row, I am filling the second state, psi 2, and all are in upspin, psi 2 state, space is psi 2 state, and particle is in the upspin. Okay, and the third one is second state, psi 2 state itself, but particle is in the down state, downspin, right? Beta, that is beta. Now we have to fill the particles, right? So in the column, same particles, that is, this will be 1, this will be 1, this will be 1. Here this is 1, this is 1. Here it will be 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, right? So we got the Slater determinant. Why we are not specifying the upspin or downspin of psi 1 state is because it can have any state. It is not restricted by Pauli's exclusion principle, right? That is why we are writing like this. Now the fourth example. Here there are 2 states, psi 1 and psi 2, and now in the ground state or psi 1 state, 2 particles are there, and in the psi 2 state, only 1 particle. So how we can write this Slater determinant? That is equal to, there are 3 particles, so the normalization constant will be root 3 factorial, and the determinant will be a 3 by 3 determinant because there are 3 particles, right? So first is psi 2. So in psi 2 state, there is 1 particle, and this particle can have upspin or downspin. Now we have to write the particle in the psi 1 state, that is psi 1, and the particle may be in upspin, psi 1 upspin, psi 1 upspin, right? Rows contain same state, right? And the second one, state is psi 1, but spin is down. Okay, spin is down. And the last stage, that is psi 2. And in psi 2, this particle can have any of upspin or downspin. So we are just writing its space part only. Okay. Now we know in column we have to fill same particle. So this one is first particle. That is first particle is in the up state. First particle. Here this is second column. So second particle, second one. Okay. And this one is third column, third particle. Okay. So this will be the slated determinant for this kind of distribution. Now the last example problem, that is there are two states, psi 1, psi 2, and two particles in psi 1 state, two particles in psi 2 state. So there are total 4 particles. Therefore the wave function psi will be 1 by root 4 factorial. That is the number of particles, right? And the determinant will be a 4 by 4 determinant. Now, first we are considering the state. Space part is this one, that is psi 1. And the particles in psi 1 state can occupy in two states. One is upspin or in downspin, right? So first is upspin case. Psi 1 upspin, psi 1 upspin, psi 1 upspin. Now particle can have in downspin, that is psi 1 downspin, psi 1 downspin, psi 1 downspin, psi 1 downspin. Now let us consider the second one, that is psi 2. Space part is psi 2. So in psi 2 also particle can occupy in two states. One is upspin or in downspin. Okay, so this one is psi 2 upspin, psi 2 upspin, psi 2 upspin, psi 2 upspin. And the particle can occupy downspin also, that is psi 2 beta, psi 2 beta, psi 2 beta, psi 2 beta. And I told you in column the particle will be same, that is this will be first particle, right? And this will be second particle, this will be third particle. See, there are total 4 particles, right? And this will be fourth particle. Okay. So this is the Slater determinant for this stage. Here we are discussing about identical particles. With the spin, right? That is, we know fermions are there and bosons are there. Both have spin, right? And we know the fermions obey Pauli's exclusion principle. That is, no two electrons or fermions can have all the 4 quantum numbers. That is, what are the quantum numbers? S is there and ms is there. That is, spin is there and orientation of spin is there. That is ms. Okay. That means if particle spin is half, then it will have 2 orientations. One is plus half and the other is minus half. This is ms value. This is s value. Okay. So we can fill any number of particles in a single state because of Pauli's exclusion principle. But for boson, there is no restriction. in a single state itself, you can place n number of particles. There is no restriction. This is a single state, psi1. Okay, so any number of bosons can be filled in that particular state. But here we see for fermions, we now different spin is possible. That is s equal to half is there, s equal to 3 by 2 fermions are there, s equal to 5 by 2 fermions are there. Then for a spin half fermion, there will be two orientations. That is, ms value will be plus half or minus half. So in a state, single state psi1, two fermions can occupy. Fermion with the spin half can occupy. That is, if one is in upstate, other should be in the downstate. Okay, or if it is in downstate, the other particle should be in upstate. That is the condition by Pauli's exclusion principle. That is, not all the quantum numbers will be same. See, here the ms values different for different particle, right? Here it is minus half, here it is plus half. So they all the quantum numbers are not same. Spin part is different, orientation of spin part is different. Okay, so in a particular state psi1, two fermions can occupy. Similarly, for s equal to 3 by 2 fermion, it can occupy 4 particles. The reason is the ms values are plus 3 by 2, plus half, minus half, and minus 3 by 2 are possible. Okay, and similarly for this one, ms value can have plus 5 by 2, plus 3 by 2, plus 1 by 2, minus half, minus 3 by 2, minus 5 by 2. So total 6 particles can occupy in this state. That means if one of the particle is in plus 5 by 2 orientation, other should be in plus 3 by 2 orientation, other should be in plus 1 by 2 orientation, other is 1 by 2 orientation, minus 3 by 2 orientation, and last one will be in minus 5 by 2 orientation. Okay, so if again one more particle is coming with the same spin, it can occupy in the same state. It will go to other state, right? And the multiplicity of states is given by a general expression, that is 2s plus 1. So for s equal to half, you substitute this half value here. So 2 into half plus 1, that is 2. That is, see, 2 particles. And just substitute s equal to 3 by 2 here. So you will get 3 plus 1, that is 4. And substitute 5 by 2 here. You will get 2 into 5 by 2 plus 1, that is 5 plus 1, 6. Okay, so here the maximum number of particles is equal to 2. Here the maximum number of particles in same state, that is in same space state, is 4. Here maximum number of particles in the same space state is 6. Okay, let us discuss an example problem. Find the energies of two non-interacting identical particles in the ground state and first excited state of 1D box. First we have to know about 1D box and its energies. That is, I think you already familiar with this one, right? Suppose there is a 1D box of length 0 to L, then the energy levels, different energy levels are n equal to n square pi square h square by 2ml square. Suppose I am writing this terms as E1, that is n square E1. Okay, so this is the ground state. For ground state, n value is equal to 1. So the energy will be E1. Okay, second, first excited state. For first excited state, n equal to 2. That is, n square is 4 E1. And the other state, that is second excited state, n is equal to 3. That is 3 square E1. That is 9 E1. So these are the state psi 1, psi 2, psi 3. That is ground state, first excited state and the second excited state, and this is their corresponding energies. Okay, I think you know the wave function. The wave function will be psi n of x is equal to root 2 by L sin n pi x by L. Okay, so first we are going to discuss for bosons. We know for bosons there is no restrictions. Any number of particles can have in any state. So first let us consider the ground state. This is the ground state, that is the energy is E1. This is first excited state, that is energy is 4E1. So both the particles are in the lowest energy state, that is the ground state, right? So what will be the energy? That is E will be, E ground state energy will be is equal to, two particles are there and both have same energy E1. So the total energy will be 2E1. Now let's consider the first excited state. So these are the two states. This is E1 state for E1. Okay, so first here this particle is jumping to the higher energy state, that is phi. So the total energy, that is the first existed energy, is equal to one of the particles is in the E1 state, that is E1 plus 4E1, that is 5E1. Now let us consider one more state, that is second excited state. That is, these are two states with the energies E1 and 4E1. So now the other particle is also jumping to the higher state. So both the particles are the 4E1 state. So the energy of second excited state will be equal to 2 into 4E1, that is 8E1. Now let us discuss second case. Second case is for fermions, spin half fermions. We know by Pauli's exclusion principle, maximum number of fermions in a single state is 2. So let us consider the ground state. So these are the two states of a 1D box, that is E1 and 4E1 energies. So both the fermions are in the ground state, lowest energy state, that is the energy E ground state energy is equal to 2E1. Now let us consider the first excited state, that is one of the particle is jumping to higher state. So this is the arrangement. This is E1 state, this is 4E1 state. So energy of first excited state is E1 plus 4E1. Okay, that is 5E1. Next one, that is second excited state. These are the states with the energies E1 and 4E1, and here now this particle is also jumping to higher state. So both the particles are in the 4E1 state. Therefore energy of second excited state is equal to the energy of this particle plus energy of this particle, that is 2 into 4E1, 8E1. Now let us consider another case. Here we have spin half fermions, but one more condition is there. Here both the spins are same. That is, if sigma 1 is up spin plus half, sigma 2 is also equal to plus half, or sigma 1 is minus half, that is spin down state, sigma 2, the other particle is also in the spin down state. Okay, so both the particles are in same spin state. Okay, so this is the condition now. Now what is the ground state? So the states are these two, E1 and 4E1, and the ground state means both the particles in lowest energy state. So I am filling the first particle here. Now I want to fill the other particle. See, by Pauli's exclusion principle, no two fermions can have, or no two electrons can have all the same quantum state. Here both of them have same spin. Suppose I am taking both the particle having plus half spin. Okay, so this particle is in the plus half spin. So another particle will not occupy the same even state. It goes to the next higher energy state. Okay, spin up state, right? Because both of them cannot occupy the same state because of Pauli's exclusion principle. So what will be the ground state energy? That will be equal to one particle is in the E1, so E1 plus for E1, that is ground state energy is equal to 5 E1. Now let us check what is the first excited state. See, this is E1 state, for E1 state, and this is 9 E1 state. By this exclusion principle, each state contains only one particle, right? So if I am filling one particle here, then this is in the spin up state. So I am taking this particle to the next higher state. Okay, this is also in spin up state. So what will be the total energy? That is E first excited state, that will be equal to 9 plus 1, that is 10 E1. Okay, now let's check second excited state. This is E1 state, for E1 state, 9 E1 state. Now I am taking this particle to the next higher state, that is, this is the arrangement. So the second excited state energy will be 4 plus 9, that is 13 E1. That is, ground state will have energy 5 E1, first excited state will have energy 10 E1, and the second excited state will have energy 13 E1. Okay. Now let us consider another example problem. There are 5 identical non-interacting particles and are confined to a 1D box of length L. And the question is to find the ground state and the first excited state energies. If the particles are bosons, spin half fermions in state, that is, this is S, MS. Okay, that is, spin is down. Both the particles are in down spin. All the particles are in down spin. Okay, and the spin 3/2 fermions. So first we are going to discuss about question A about bosons. Okay, so this energy states of 1D box is E1 and 4E1. This is the, okay. Here the first case, consider 5 identical particles and all are bosons. So we can fill all the 5 bosons in the E1 energy state, because for bosons there is no restrictions. So what will be the ground state? This is the ground state distribution. So the ground state energy will be E ground state is equal to 5 E1. Now let us check what will be the first excited state. So these are the states E1 and 4 E1. So one of the boson in the E1 state is jumping to 4 E1 state. So the remaining 4 will be here in the E1 state and 1 will be in the 4 E1 state. So energy of first excited state will be 4 E1, that is 4 particles are in E1 state plus 1 particle is in the 4 E1 state, 1 into 4 E1, that is energy is 8 E1. Okay, now I am going to consider spin half fermions. Not the second case, an intermediate step between second case, that is this one. Okay, so before, this is a specific case, that is all these particles are in down spin, but here I am generally taking spin half fermions, so it may be in up spin or it may be in down spin. So what will be the ground state energy? These are the different energy levels of 1D box, that is E1, 4 E1, 9 E1. There are total 5 fermions, right? So each state can contain maximum 2. That is, one will be in the up state, then other will be in the down state. down spin state, right? So this will be the arrangement. So the ground state energy will be equal to 2E1 plus 2 into 4E1 plus 9E1. Now let us check the first excited state. So which of the particle jump to higher state? Is from ground state or from this state? From this state the particle will jump. So only last the particles in the ground state will jump to higher state, because ground state particle have more stability. So when particles are jumping to higher state, the ground state particle have minimum priority, lowest priority. So, okay, that is why the particle in the first excited state is jumping to the next higher state. So in 9E1 state, 4E1 and the E1 state. In 9E1 state, 2 particle will be there, and 4E1, 1 particle is there, and the E1 state, 2 particle will be there. That is, energy of first excited state will be equal to 2 into E1 plus 4E1 plus 2 into 9E1. Okay. Now let us consider the case B, that is spin half fermions in state half minus half. That is, this is S value and this is MS value. That is, the orientation of the particle is down, right? Spin down particle. Okay. So all the 5 particles are spin down particles. So what will be the ground state? So see, all are in the same state. Therefore, each state can occupy only one fermion, right? That is, ground state means there will be 5 states. So each particle occupy each state. That is, this is E1 state, 4E1, 9E1, 16E1 and the 25E1. So the total energy is sum of all these energies. That is, ground state energy will be equal to 55E1. Now let us consider the first excited state. So there is 1, 2, 3, 4, 5, 6 states. Okay, so this is E1 state, this is 4E1 state, this is 9E1 state, 16E1, 25E1 and the 36E1. So this particle will jump to the next higher state. Okay, so it will be here, and in 25E1 there is no particle. Here also, here will be particles. Okay, so the total energy will be E first excited state will be equal to 61E1, right? Now let us check the case of spin 3/2 fermion. That is, S value is 3/2, therefore MS values are plus 3/2 plus 1/2 minus 1/2 and the minus 3/2. That is, each state can occupy 2s plus 1, that is 4, right? That is, these are the 4 spin state of a spin 3/2 fermion. That is the orientation, right? So 4 orientations are possible. So each state can contain maximum of 4 spin 3/2 fermions. So this is the ground state. This is E1 and this is 4E1. So there are total 5 spin 3/2 fermions. So the 4 of them can be accommodated in E1 state. Then the other one will jump to other state. That is 4E1. So the ground state energy is equal to 4E1 plus 4E1. That is 8E1. Now let's take the first excited state. In first excited state, one of the spin half fermion jump to the next higher state. That is, 2 will occupy here and 3 will be here. So the ground state, sorry, first excited state energy is equal to 3E1 plus 2 into 4E1. Okay. Next, we are going to discuss about 5 identical particles in 2D box. So first we have to now about energy levels of 2D box. This one is also we already discussed. Again, let us discuss the energies of 2D box. What is the expression for energy? That is nx square plus ny square into pi square h square by 2ml square if length of the box is L. Okay. So if you are writing this as E, then this is equal to nx square plus ny square into E. And there we already find out this degeneracy of different state, and the ground state is non-degenerate. First excited state is doubly degenerate. Second excited state is non-degenerate. Third excited state is doubly degenerate, and the other state is also doubly degenerate. This is the order of degeneracy. Okay. And what is the energy levels? See, the nx can have values 1, 2, 3, etc. and ny can have values 1, 2, 3, etc. So different combination of this nx and ny will give different energy states. So the first combination is 1, 1 combination. That is nx equal to 1 and ny equal to 1. So we get energy E is equal to 2 E, right? And next one is nx equal to 1, ny equal to 2. So the energy is 4 plus 1, that is 5 E. See, another combination of that is nx is equal to 2 and ny is 1, then also we will get energy is equal to 5 E. This is the first excited state, right? And it is doubly degenerate. Here this is ground state and it is degeneracy is 1. Okay. 1. Okay. First excited state is 2. Now, third combination, that is nx equal to 2, ny equal to 2. Therefore, the energy will be equal to 8E. That is second excited state. See, it is non-degenerate. Okay, that is 1 to 1. Similarly, you can take the other combination, next higher combination, that is nx equal to 1, ny equal to 3. Therefore, you will get energy is equal to 10E. And if a combination of nx equal to 3, ny equal to 1, also you will get energy is equal to 10. That is third excited state is doubly degenerate, right? And the another combination of nx and ny is nx can have a value 2, ny can have value 3. Therefore, energy is equal to 9 plus 4, that is 13E. And if nx equal to 3 and ny is equal to 2, then also we will get energy is equal to 13E. So here also it is doubly degenerate, and this is fourth excited state. This one, right? That means if you are drawing a diagram, it will look like this one. This is the ground state, and the ground state is non-degenerate. Now this is first excited state. This first excited state is doubly degenerate. Okay, that is ground state is nx equal to 1, 1. First excited state, there is two combination. One is 1, 2 and one is 2, 1. Okay, both have same energy, that is 5e. Here it is 2e. Next is second excited state. It is non-degenerate, that is 2, 2. Okay, that is energy is 8e. The other one is third excited state, and it is doubly degenerate. So for nx combination may be 1, 3 or 3, 1. So the energy will be, for both the state, energy will be 10e. Okay. Now you are familiar with the energy levels and the degeneracy of states of a 2D box. Now let us consider boson. 5 bosons are there, and these 5 bosons are in a 2D box. So the ground state energy of a 2D box is 2e, and I told you for bosons there is no restriction. So any number of bosons can be filled in the any state. Okay, so this is the ground state. So for ground state, all the 5 bosons will be in the lowest state. That is total energy E, ground state energy will be 10e. Now let us consider the first excited state. That is, this is the energy diagram. Ground state is there. It is energy is 2e, and first excited state is there, and it corresponds to, it is degenerate state. It corresponds to 2 combination of nx and ny, that is 1, 2 and 2, 1. Okay, and both of the state will have the same energy, that is 5e, 5e. That is, it is a degenerate energy state. Now one of the boson in the 2e energy state will jump to higher energy state. Okay, so there will be, in ground state there will be 4 bosons, and in the next higher energy state 1 boson will be there. Okay, so the E, first excited state, equal to, there are 4 particles in the ground state, that is in the 2e state, that is 4 into 2e plus 5e. 1 particle is in the 5e state. Okay, so you will get the, energy in the first excited state, that is 13e, right? Now let us discuss about spin half fermions. First we are going to find out the ground state energy, and the energy diagram is like this one for 2D box. Okay, this is 2e, and this is 5e, this one is also 5e. So by Pauli's exclusion principle, maximum number of fermions, spin half fermions in each state is 2. Okay, so 2 will be here, 2 will be here, and remaining 1 will be here. So the mg, ground state mg, is equal to 2 into 2e plus 2 into 5e plus 5e. Now second one is first excited state. So the highest energy state particle will jump to the next higher energy level, that is this is 2e, that is ground state, first excited state, and the second excited state of a 2D box, right? And this energy is 5e, this energy is also 5e, and the next energy level is 80. So this is jumping to the higher state, so it will go here, right? And the remaining 2 particle in the 5e state and 2 particle in the ground state. So the energy of first excited state of this 5 identical particle in a 2D box will be 2 into 2e plus 2 into 5e plus 80. Okay. Next one is spin 3 by 2 fermions. That is the multiplicity is 2s plus 1, that is equal to 4. That is, each state can occupy maximum of 4 spin 3 by 2 fermions. So the ground state. This is the 2D box energy levels, that is 2E and 5E, 5E. There are total 5 identical spin 3 by 2 fermions. So 4 of them can occupy in the 2E energy, then next will occupy in the 5E state. That is, ground state energy of this distribution will be 13E. Now let us consider the first excited state. That is, these are the energy levels. This is W degenerate, then it is non-degenerate, right? Okay, so this one will jump to the next higher state. Okay, why this one is jumping? Why the particle in the 2E energy state is not jumping to higher state? Because the lowest energy state is 2E energy state. So the particles in the lowest energy state will have more stability. So they try to occupy that lowest energy state for more time. So first the higher state particle will jump to or go to further higher energy states. Okay. So all this will be here itself. All the 4 particles will be here, and the next one will be jump to the higher state. That is, this is 2E state. These are 5E, 5E state, and next one is 8E state. So the energy of first excited state will be 80 plus 80, that is 16E. Now let us consider another example problem. Here 5 identical non-interacting particles are confined to 1D LHO, linear harmonic oscillator. Earlier we discussed about 1D box and the 2D box. Here the particles are now in 1D linear harmonic oscillator. Okay, find the energies of ground state and first excited state if the particles are boson, spin half fermions with the spin state half minus half, and spin 3 by 2 fermions. So to solve this problem, first we have to know the energy levels. Energy levels of 1D linear harmonic oscillator. I think you are remembering the expression for energy of 1D linear harmonic oscillator, that is E n equal to n plus half h cross omega. Here n can have values 0, 1, 2, 3, etc. Right? So the different energy levels are, if n equal to 0, energy will be half h cross omega, and if n equal to 1, the energy will be 3 by 2 h cross omega, and if n equal to 2, energy will be 5 by 2 h cross omega, and if n equal to 3, energy will be 7 by 2 h cross omega, and so on. Okay. So now we know the energy levels of 1D LHO. Now we can solve the problem. First consider bosons. There are 5 bosons, right? And I told you there is no restriction for bosons. So any number of bosons can be filled in any state. So in the ground state, the lowest energy state is n equal to 0, that is half h cross omega. All the 5 particle bosons can be placed in the half h cross omega state. That is the total energy, that is ground state energy will be 5 by 2 h cross omega. Now let us consider the first excited state. That is, this one of the particles is jumping to the higher energy level. That is half h cross omega, and next higher energy level is 3 by 2 h cross omega. So here one of the particles jump to higher state, so it reaches here, and remaining 4 are in the half h cross omega. Okay, so you will get the first excited state Nc. That is, there are 4 particles in the half h cross state plus 1 particle in the 3 by 2 h cross omega state. Now let us consider spin half. That is, next question is spin half fermions. So for spin half fermions, you know maximum number of particle in each state is 2. So these are the various states. First we have to consider the ground state. So these are the various energy levels in a 1D LHO, that is half h cross omega, 3 by 2 h cross omega, 5 by 2 h cross omega. So there are total 5 particles. So 2 can fill here, next 2 can fill here, and 1 fill here. That is, ground state energy is equal to 2 particle in half h cross omega state plus 2 particle in 3 by 2 h cross omega mg plus 1 particle in 5 by 2 h cross omega mc. So you will get the ground state mc. Now let us consider the first excited state. That is, this one will jump to the next higher state. So half h cross omega, one is jumped to the other higher state. So only 1 in 3 by 2 h cross omega and 2 will be here. That is 5 by 2 h cross omega. So by add these energies, you will get the energy of first excited state. Maybe you have a doubt why this one is not jumping to the higher state instead of this one. The reason is, if this one is jumping to the higher state, then you will get a very high energy value. In between that energy value, ground state, and that energy value, there is a, in between, there is one energy value. That energy value corresponds to this distribution of particle. Okay, that is why this is the next energy level. That is, this is the distribution gives the lowest energy level, and this one is the distribution giving the next higher energy level. Okay. Now let us consider the spin half fermions in the state half minus half. That is, spin orientation is down, right? That is, all the 5 spin half fermions are in down spin state. Okay, so this is, let us write the ground state. This is the different energy levels. Half h cross omega, 3 by 2 h cross omega, 5 by 2 h cross omega, 7 by 2 h cross omega, and the 9 by 2 h cross omega. Here you see all the fermions, all the particles are in spin up state. Okay, therefore by Pauli's exclusion principle, each state can occupy only 1. Okay, therefore here there will be 1 particle, here will be 1 fermion, here will be 1, and here will be 1. So 5 fermions will occupy like this. So you can find out the ground state energy, that is equal to this energy plus this energy plus this one plus this one plus this one, because each of state contain only 1 particle. Now first excited state, that is, this particle will jump to the next higher energy level. That is, this is half h cross omega, 3 by 2 h cross omega, 5 by 2 h cross omega, 7 by 2 h cross omega, 9 by 2 h cross omega, and 11 by 2 h cross omega. So this, here one fermion will be there, here also one will be there, and the fermion in this state will jump to the next higher state. Okay, so you can find out the energy of first excited state by adding all these energies. So please do this. This is a work for you. Now I am going to introduce two terms. One is Fermi level and other is Fermi energy. Is both are same or both are different? And what is the meaning of Fermi level and what is Fermi energy? I tell you those things in this session. Before that, we need to consider an example. An example of 6 electrons in a 1D box. Okay, so you are already familiar with the energy levels of a 1D box. That is, ground state energy is E1, first excess state is for E1 and next one is 9. So 6 electrons are filling in the states. This is the ground state. So filling like this. Okay. Now someone is asking you what is the Fermi level of this distribution, arrangement of particles. Here Fermi level means it is about a level. That is, this one is one of the level, this is next level, this is the next level, right? So the level is 9E1. That is the last level occupied by electron. That is Fermi level. That is 9E1. Okay, the last electron is occupied in the level that is called Fermi level. Here that is 9E1. Okay. Last occupied level is called Fermi level. Now next one is, what is Fermi energy? That is represented by EF. What is Fermi energy? Fermi energy is the total energy of Fermi level. That is, there are two particles in the Fermi level 9E1. Therefore, the Fermi energy of the system is 2 into 9E. That is 18E1. If there is only one particle in the Fermi level, then Fermi energy will be 9E1. But here there are two. So, the total energy of that level is called Fermi energy. Suppose there are only 5 particles. Okay, then 2 particle will be here, 2 particle will be here, 1 particle will be here. So this is E1 for E1 and this one is 9E1. Now, what is the Fermi level? That is the last occupied level. That is this one, right? That is Fermi level is 9E. And what is the Fermi energy? See, in the last level, only one particle is occupied. Okay, so 1 into 9E1. Okay, that is 9E1. I think now the idea is clear.